This data visualization maps out the brutal baseline of modern medicine. Bringing just one new drug to the market requires waiting an entire decade and spending roughly $2.6 billion. Even with that level of investment, nearly 90% of these drug candidates fail during the final stages of development. These late-stage failures happen because our most powerful supercomputers cannot accurately predict how complex molecules behave inside a living human body. As long as researchers rely on computational guesswork, the medical pipeline will remain restricted by this massive financial and temporal bottleneck. The devices we use today operate on binary, a language of zeros and ones. They solve problems like a train on a track, checking one possible route at a time. This linear approach fails. Biological molecules contain millions of unpredictable electron interactions happening simultaneously, a complexity binary logic cannot map. To simulate a moderately complex molecule using these paths, a supercomputer would need to be larger than the known universe. Standard technology has hit a hard physical wall, leaving the most intricate secrets of human biology out of reach. To bypass this limit, scientists are moving away from traditional bits in favor of the subatomic quantum qubit. This replaces the rigid binary switch with a continuous sphere of possibilities, allowing a qubit to exist as a 0 and 1 simultaneously. Because of this superposition, it tests millions of molecular combinations at once, rather than sequentially. This collapse of sequential trial and error turns years of calculation into a single computational moment. To properly synchronize these possibilities, quantum computers use entanglement, which links these multi-state qubits into a single cohesive system. Since these machines operate on the same subatomic laws as human cells, they can mimic how nature actually functions with perfect fidelity. As physicist Richard Feynman once observed, nature isn't classical, so a true simulation of nature must be quantum mechanical. This architecture allows medicine to transition from relying on rough approximations to utilizing biological simulators. This timeline visualization shows how quantum simulation compresses the early design phase, a process that normally consumes up to 5 years of lab work, into a matter of days. Removing this digital bottleneck allows the industry to move away from generic, mass-produced pills. Quantum algorithms will be able to analyze an individual's exact DNA to engineer custom medicines tailored to their specific body. Healthcare is shifting toward a model of hyper-personalized engineering, where treatments are designed to match a patient's unique genetic sequence. This processing power gives us the ability to model the complex proteins behind currently incurable diseases, including Alzheimer's, Parkinson's, and aggressive cancers. Tech giants and pharmaceutical companies are already building the quantum infrastructure necessary to run these simulations. In the future, when a new global health crisis emerges, we will be able to design a targeted cure in days rather than years. As these systems come online, we're left to consider which incurable disease this technology will conquer first. Let us know your thoughts in the comments below.